Good evening, everyone. Welcome to Professor Srikanth Nehru from University of Hyderabad.
Thank you. I am listening. Please go ahead. It's already 6.
Okay. So welcome back to day two of our faculty development program on innovative green energy generation and storage technologies. I hope you all enjoyed the sessions yesterday and are excited for today's topic. Yesterday, we explored advancements in renewable energy sources and also explored solar energy system and applications. We have two interesting sessions planned for today. The first session will focus on energy storage materials. The speaker for this session is Professor VVSS Srikanth, School of Engineering Sciences and Technology, University of Hyderabad, an expert in surface and interface engineering, nanoscience and technology, the development of innovative materials for energy storage and environmental applications. Professor Srikanth will share valuable insights into the energy storage materials today. The second session will focus on how renewable energy systems are designed and how new ideas and technologies are making these systems more efficient and reliable. Now, this session will led by Dr. Sarvottam Jyoti, Associate Professor, NIT Calicut. I encourage everyone to participate actively, interact with experts, and share your thoughts during the sessions. Let's begin with our first session. Please join me in welcoming Professor Srikanth, who will share his thoughts and insights on energy storage materials. We are truly honored to have him with us today to share his expertise in this important field. Before we dive into this session, I would like to invite our session coordinator, Dr. K. Ravi Kumar, to formally introduce today's esteemed speaker. Over to you, Dr. K. Ravi Kumar, to share more about our distinguished speaker. Thank you.
Thank you, sir. So let me introduce his biodata. So, good evening, everyone. It is my privilege to introduce an eminent professor and distinguished
And
researcher.
Dr. Ravi, if I may interrupt,
Sir.
we'll skip this. I'm good with. I'm a professor in the University of Hyderabad. That should be good enough.
Sir, okay.
Let's start. I mean, you're all right. We'll go ahead. This can be circulated if it is required, or otherwise they can find it on the website. Let's not
Okay.
spend time on this.
Okay, sir.
Let's yeah.
Okay,
Just
So
Professor
like
should I
Srikanth.
start?
formal.
I mean, if
Yes, sir. You
it's
can
okay, it's
continue.
a formal. I know
Yes,
it's a
sir.
formal
Okay.
thing. That's it's but okay. I think we'll save a few minutes, so
Okay.
we can
Okay,
spend
sir.
those minutes on question and answers or discussion. So
Okay,
let's
sure.
let's go ahead. Let me share my. I think you should allow me to share my PPT, and then I'll start.
It's allowed, sir.
Yeah, is it visible?
It is visible.
Yes, sir. It's visible, sir.
But it's not on the this one, right? I mean,
Not the
the
slide mode.
yeah. So now,
Yes. Screen share.
okay,
Okay. Fine now.
yeah. Am I visible?
Yes.
No, I think my video is not on.
No,
Let
no.
yeah.
One
So
time.
now, am I visible?
Yes, sir.
Visible, visible.
Okay. So this is how I look. I don't look like a professor, but yeah, cannot help. Good afternoon, good evening, everyone. I thank the organizers at MVGR College of Engineering for inviting me to this ATAL FDP program. Um, Firstly, let me congratulate the college, MVGR College of Engineering for selecting such an important topic for the FDP. I also thank the coordinator, Professor Subramaniam, and also Professor Rajkumar for taking care of the arrangements and bringing in so many participants into the program. I saw the list of presentations to be given, and so then I thought it is very important for me to share my thoughts on the title, or the present title, which is Green Energy as Green as it claims to be. If I'm disappointing some people, I'm sorry, because I changed this title looking at all the topics in the FDP program. General characterization techniques for material storage, the energy storage devices and all is a regular thing. But I wanted to, the premise of selecting this topic for this FDP is to throw a light on the importance of understanding the philosophy of green energy. Another premise of choosing this presentation uh, is to bring out different lacunae, the problems associated with various green energy technologies, because many of us use this term green energy, green, so loosely, and actually it's actually a green watershed, because if you see the true definition of green energy, it's really complicated and it involves so many things. So, as I said, the second premise is to bring out the problems associated with the green energy technologies, and I will not just pose the problems and highlight the problems, but I also have some recommendations, for those who wish to work in green energy technologies, wish to read green energy technologies, wish to conduct research in green energy technologies, wish to teach green energy technologies. Okay? So I'll present my views, and then we can have a discussion at the end of the talk. My presentation basically will start with simple energy needs, energy consumption in some numbers, and then I'll bring in the concept of sustainability, and then I'll use some slides to discuss about the basic definitions, because we go so much forward in research or reading and claiming something to be green, but we don't comprehend the basic definitions. Okay, so I have a couple of slides on definitions, and you'll see that if we consider strictly the definitions of clean, renewable, and green energies, there is a subtle difference, and we have to be very careful in using the terminology green energy and green energy technologies. Uh, I'll consider three examples: one related to energy storage, one related to energy conversion, one related to energy storage, and one related to energy transmission or transportation, to highlight the lacunae or different problems associated with green energy, the so-called green energy technologies. And then I have recommendations, especially these recommendations I've consolidated for the sake of academicians and researchers who wish to, who are working or wish to work in this area. Uh, uh, Professor Subbu, am I clear?
Clear, sir. Clear, clear, clear.
Okay. Yeah. So let me start, hoping that it is also clear for others. So once in a while, I'll be asking Subbu if I'm clear, because I'm the only one with, nobody else is speaking, and I'm the only one giving the presentation. Okay. Yeah. So let's start with the energy consumption, and try to understand the energy requirements for the future. As of now, on this planet, we actually consume about 580 million terajoules per year of energy, and by 2050, we are in the requirement of 900 million terajoules. So million is 10 power 6, tera is 10 power 12. Okay. So if you cannot comprehend that, I have a simple example here. So if I were to travel from India to USA, that is about 100,000 kilometers by a specific Boeing 787, 737, the energy expended or spent is about 1 terajoule. That is 1 multiplied by 10 power 12 joules. Okay. So you see, we are in the requirement of so much of energy, that is 900 multiplied by 10 power 6 multiplied by 10 power 12 joules uh, per year by 2050. And the idea is, okay, the requirement on one hand is good. We buy uh, if we want to meet this requirement of 900 million terajoules per year, uh, we are talking about bulk energy conversion, bulk energy storage, bulk energy transportation, and all this without harming the environment. So, if we consider 900 billion terajoules per year requirement of energy requirement by 2050, so while protecting to protect the environment, we should also know how much of uh, greenhouse gases are produced if we were thinking of expanding 900 million terajoules of energy per year, let's say in 2050. So that is about 50 billion metric tons of greenhouse gases per year. Now, 50 billion is 10 power 9, metric ton is 1000 kilograms. Out of this, about 35 billion metric tons is of only carbon dioxide. Okay, so prepared for so much of carbon dioxide emission, greenhouse gases emission here, when we are saying want to expend 900 million terajoules of energy. Now, this is where these an amalgam of United Nations has come up with this SDG, Sustainable Development Goals. There are 17 such goals which many of the countries in the world have agreed to work on. And in each of these sustainable development goals, there are several tasks, and totally about 169 tasks covering 17 sustainable goals. Now, all the institutions in various countries, governmental, non-governmental, academic, research institutions, they are working. This has become a buzzword and it has become so important. Many institutions are working on achieving these sustainable development goals. Now, the problem here is these goals are interrelated. For example, if you don't achieve quality education as a goal, several you will fail in several of these sustainability developments. If you fail in, let's say, development goal 3, which is good health, if you want to achieve good health and well-being, if you fail in, let's say, clean and sanitation, if you fail in sanitation, you'll fail in good health and well-being. No, as far as this FP concerned, the faculty development program is concerned, and goal 7 is very important, which is affordable and energy. And you should notice on this slide that UN, United Nations, has not used anything called green energy. They have used the word clean energy. So that is what I wanted to insist on. The usage of terminology has to be uh, uh, very clear. Unless we comprehend the meaning of what this clean energy, green energy, renewable energy is, we should not loosely use. Okay. So if you see this, if you want to achieve affordable and clean energy goal, several other SDG goals are involved. If I cannot learn what the energy is, what clean energy is, that comes under quality education. If you don't do quality education, no matter what it will be not up to the mark, and therefore you can never achieve affordable and clean energy or any other SDG. Okay, so seven, as I said, is very important. Oh, what is that? Slides are not moving. Oh, sorry. Okay. Okay, so the seven is very important. Let's see how we are doing in the overall score in the India. Okay, so unfortunately, we were to achieve these SDGs by 2030. Okay, and we are now in 2025 or 2024, and we are not even close to 50% the overall in the world. Okay, so but the idea was to achieve 100% by 2030, so that while expending, while storing, while transporting so much of energy, we are actually protecting our planet in various aspects. In doing so, some countries perform well. For example, Finland, Germany, Japan, close to 80% than 80%, but throughout the world it is less than 50, but as a country we are doing slightly better than the average. Now when it comes to renewable energy, but I'll be coming back to these definitions, but I'm using the terminology. You should notice that at different places I'm at one place I'm using clean energy, at other place I'm using renewable energy. Okay, so if you see the renewable energy, the use of renewable energy, use of renewable energy in total energy consumption. Okay, India is, not so bad actually. In various renewable energy technologies in its day-to-day life, and thereby we are actually in the fifth place, close to Germany. Okay, and if you see United States, which is doing very bad in comparison to India in incorporating renewable energy technologies in their day-to-day life. But you see the countries like United States, which is a superpower, always tells other countries to incorporate renewable energies and reduce carbon footprint. Okay, so we are actually doing well as per the United Nations as far as using renewable energy technologies in total energy consumption in a day-to-day basis. And when I say total energy, it is total energy is all that is related to renewable energy, and we'll see the definitions. Okay, there is a subtle difference, as I said, between among the clean, renewable, and green energy, and we'll see with an example, with the example as well. Now, please carefully look at the slide, and I'll have to read. Clean energy is the energy when expanded produces ideally no greenhouse gas emissions. The best example is solar energy. When it is converted into electrical energy, there are no greenhouse gas emissions. Therefore, solar energy can be an example of clean energy. Then what is renewable energy? Renewable energy is the energy converted from renewable from a renewable source or from renewable sources. So solar energy is again an example where in this case it's a renewable form of energy. So the light is a renewable source. So therefore the energy that is converted can be considered, or the energy, as I said, solar to electrical. The source is renewable, so you call that as a solar energy as renewable energy. So you can call solar energy as clean energy and renewable energy. Then what is green energy? Okay, green energy is the energy converted from one form to the other, or energy expended. That means you use any form of energy without ideally harming the environment. Okay, but you can say when we are converting solar energy to electrical energy, we said greenhouse gas emissions are not there. But if you see the green energy definition, And if you consider building up the manufacturing the solar panels, mining the silicon, fabricating the solar cells, and all this actually involves harming the environment. So, in other words, clean and renewable energies need not be always green. Okay, so that means if I have a solar energy technology, solar energy is clean and renewable, but it is not a green energy technology, because in the whole life cycle of the solar cell, you're actually harming the environment. We'll have some numbers, then you'll be at least some of you might it will be a shock to some of you, or maybe many of you. Okay, so the takeout point here is clean and renewable. There is a difference between the nomenclature. Clean energy is different from renewable energy, green energy. And the other takeout point is clean and renewable energies need not always be green. Okay. Is there any technology in that case which is clean, renewable, and green? There is actually only one technology that actually is this photosynthesis. Okay, which happens in with the help of chlorophyll in plants. They take light energy, they convert into sugars, which is conversion into chemical. Mass is a manifestation of energy. It gets converted into sugars, and in doing so, is the environment harmed? No, in fact, it is the opposite. The environments get benefit. The carbon dioxide in the environment is taken up in the during the photosynthesis, and oxygen is released. So probably this is the only example which satisfies. Photosynthesis is a technology, but it is in the technology run by nature, not by the humans. So we humans, even after so many years, we could not actually replicate photosynthesis. Artificial photosynthesis, you might have heard about it. Not even 10%, not even 20% of the ideal photosynthesis that takes place in the nature. Okay, this is the only example. Basically, there is a clean because it's solar, renewable because it is light, it is always available, and then green because it is not harming the environment. Now, but consider this. This is our a big huge building in our university. It is a school of life sciences. You see so many solar panels. These are grid connected solar panels. It is about these 1100 kilowatt peak solar panels connected to an inverter, 100 kilowatt inverter, and generating about 1.6 million units per year. Okay. Now, uh, when we consider 1.6 billion units, that is one unit is 1 kilowatt hour. You are actually having a carbon dioxide savings of about 1300 kilograms per year. Okay, that's 1300 tons per year. That is a huge number. Okay, but you see, carefully see this example. I need so many panels. That means I need so much of silicon. So I need to mine silicon. Mining silicon involves pollution. That means environmentally not friendly. And okay, the moment it works, it probably produces energy, converts solar energy to electrical energy. But to get to this point, there is a disastrous process. It involves chemicals. It involves leaving the chemicals, unreacted chemicals, into the environment, mining, and then once these panels are done, I mean they age and then they stop working. Where do you dump them? Okay, that's a big problem. And in fact, the solar waste, that is the solar cell waste that is obtained post the life of these panels is much greater than a problem than plastic. Okay. Yes, it is a clean energy because the solar energy is converted into electrical energy without the emission of greenhouse gases. Wonderful, clean energy. It is a renewable energy because the source of conversion, the primary source is the renewable source. Therefore, it can be considered as a renewable energy technology, but it is not green energy because if you consider the entire life cycle, that is from mining to the waste that is generated post the life of these panels, if you consider them, is absolutely not green. Now, uh, as I said, this is the only example for green energy technology in the world. But humans actually don't ideally work. We are always lenient. We try to reduce the. We want to always work below the ideal situation, and therefore, the humans who are working have. Slightly modified the definition. They started using minimal or acceptable environmental impact. So what is green energy technology? Any technology that enables harnessing energy. It can be conversion, it can be transmission, it can be storage, but with minimal environment impact. Okay, so we don't say ideally there cannot be any technology which doesn't give us greenhouse gases when you consider the complete life cycle. Okay, so and then any technology you take, there cannot be any technology which actually doesn't harm the environment. Okay, so ideally there cannot be a green energy technology, but only if you consider a lenient definition. When we modify the definition and use minimal environmental impact, then it is all right. Okay, so we work under this scenario. We, in the sense, the humans working, and they claim that some technology is green. That implies that the technology, when you consider the complete life cycle, affects the environment in the least possible manner. Am I clear, Professor Subbu?
Yes,
Yes, sir.
yeah,
It's
It's clear. Okay.
yes.
Uh, Now let us see the key green energy technologies. These are classified into conversion technologies, where you have solar, where light is converted into electricity, wind is converted to electricity, and then biomass, some chemical energy converted into electrical energy. Okay, and then storage technologies are there. The very popular ones are the secondary batteries, supercap, supercapacitor. These actually, the storage technologies support the conversion technologies. And then you have why support? Because many of the conversion technologies, for example, solar and wind, are intermittent. Only when solar is the light is active, light in the sense it is at a peak, you can actually convert solar light to electrical energy with high efficiency. But you may actually set up engineer a system and develop a system which actually produces more energy, but you cannot use it instantaneously. Therefore, you need storage technologies. That is why the batteries and other things come into the picture. So, storage technologies basically support the conversion technologies. And then comes these transmission technologies. For example, smart grids. For example, in you want to store, you want to also transmit from place to place. Generation. This is a well-known technology, but we are looking into all of these into the green perspective. Okay, smart grids for efficient energy distribution, accommodating fluctuating renewable energy conversion. Okay? Whenever there are fluctuations, the grid is smart. It takes care of the fluctuations, and the energy losses are prevented. Okay. In addition to these, the key green energy technologies, there are allied technologies. Okay, design is, for example, we don't often consider a design approach to develop a system. I think the next talk is about design or something. Maybe it will be covered. But these approaches, design approaches, are very important. If anything done by virtue of design, actually the mass and energy balances will be very good, and then the losses will be very very less, and so the efficiency of the system will be pretty good. So you need to develop energy efficient machines. You need to develop processes which are green. efficient monitoring and management systems, transport. So many allied technologies are there. For example, energy efficient building designs. So, there in Hyderabad, there are several green buildings where they don't use fans or lights unnecessary. Okay, they use they incorporate design based construction in the while constructing the building itself in such a way that there is naturally the light coming in, the ventilation coming in, and the usage of the electricity is reduced tremendously. Okay, so these are all come under the category of key green energy technologies. Are there? These are touted as or propagated or popularized by us as key green energy technologies. So all of these are there previously, but now we are looking them as the ones which actually give a minimal environmental effect. Now, if you take the example, I'm starting with the examples, as I said, the silicon solar cell technology. What are the problems? Solar, as I said, these solar panels, once they are wasted, that means that they run, let's say for 5, they are very well maintained, and let's say they for 10 years they were working, and post 10 years they are not working, and you have to these become panels become waste. Okay, and you see they are as high as double tonnage of all the global plastic waste. Okay, if you consider now, and I'm not saying that, I'm quoting from the international organization which actually quantifies the carbon footprint of different conversion, storage, and transmission technologies. They have calculated by considering different aspects and different countries and the total number of solar panels that are being installed. All that considered, solar panels can constitute as high as double tonnage of all the global plastic waste. What it means in layman terms, it is more dangerous than plastic waste. We are already suffering from plastic waste, but you see, on one hand, we are saying solar energy is green, solar energy is clean, solar energy is renewable. But in fact, if you consider the whole life cycle, it is more detrimental to the environment than we actually presume. Now, if you see the fossil fuel energy that is used in manufacturing them, that means you need raw materials like silicon, for example. You need to transport them, you need to process them, you need to fabricate subsystems, you have to assemble them, you have to install them, you have to maintain them. All of these have an influence. Okay, and for all of these, actually, fossil fuel is used. So to maintain, to establish, to fabricate, to maintain fossil fuel. How much? If you see here, per kilowatt hour, which is 1 unit of electricity, what we know, 45 grams of carbon dioxide equivalent is emitted. Now, if you consider just fossil fuel, in getting 1 kilowatt hour power, 1 kilo per 1 hour, it is about 1,000 grams of carbon dioxide equivalent. So, comparison to just burning fossil fuel to get unit of power, 1 unit means 1 kilowatt hour power. The carbon dioxide emission, the greenhouse gas emissions are 1,000 grams of carbon dioxide equivalent. In addition to that, solar panels is less, 45 grams only, but 40 carbon dioxide kilowatt. Now, if you consider, let's say, wind energy, is 16 grams of carbon dioxide equivalent per kilowatt hour. That means wind energy is better than than solar. Okay, now let's see the other things, use of toxic chemicals. So when I want to fabricate a silicon based solar panel, I use silicon tetrachloride. which is highly toxic, hydrogen fluoride, highly toxic, and the other elements, lead, cadmium, arsenic, all of these enter into our environment. And unfortunately, not only India, but elsewhere, even in developed countries like Germany, countries like Germany and US, there are no proper regulations to prevent the entry of these toxic chemicals and elements into the environment. Now, when it comes to, let's say, the solar panel is made, the solar panels work, and then uh, they come to the end of the life. We call them as wasted solar panels. By 2050, we are going to produce throughout the world 80 million metric tons. 80 multiplied by 10 power 6 multiplied by 1000 kilograms by 2050. Where will we put them? What will we do with such a huge dump of wasted solar panels? So these are all the problems with related to conversion. This is one example of energy conversion. We have been using this solar energy as green energy and all that, but you see, you can decide by yourself whether it is really green or not with all such problems. Another famous, you know, energy storage technology promoted as green storage technology, lithium-ion battery. Now, even the Nobel laureate received the Nobel Prize for inventing this concept. He himself said that he did not imagine that it would come to this extent, because he was always thinking that lithium is trace and it is not available so easily to everyone. Okay, now let us see some numbers. This is some of you might know this high-end Tesla model, which runs on a 100 kilowatt hour lithium-ion battery pack. Okay. Uh, uh, no, lithium-ion battery pack will have lithium, the cathode material, anode material, and the stack. So many materials are involved. I've listed them in the next slide. You will see that. Okay, let us see some numbers. 1 kilogram of battery. Okay, and I'm talking about 100 kilowatt hour lithium ion battery stack is about 300 kilograms. Okay, 300 kilograms sits on this car, the battery pack. Okay, then only it can run the way it is supposed to run. The mileage, the speed, only when 300 kilograms of battery stack, total power of that is 100 kilowatt hour, sits on that car. Now, 1 kilogram of this battery requires mining of 500 kilograms of various materials. It's not just lithium, you need nickel, you need cobalt, and so many other elements. And total, you have to mine 500 kilograms, and out of that, only 1 kilogram goes into the battery. Okay, imagine how much of pollution this might be generating. Now, you see that lithium ion battery pack, this number, and these numbers are not mine. These are through research they have published. Okay, I've also given the link at the bottom. If somebody is interested, they can go through that. If you take that 100 kilowatt hour lithium ion battery stack sitting in the car, it causes about 16,000 kilograms of carbon dioxide emission. Okay, in terms of fossil fuel, in order to make 1 liter, that lithium, if I want to make a lithium ion battery which can hold one energy equivalent of 1 liter of fossil fuel. Okay, that means some energy is stored. That energy is equivalent to 1 liter of burning 1 liter of fossil fuel. What you're doing, you are wasting 300 liters of fossil fuel equivalent. You're spending 300 liters and making a battery which can only store energy equivalent to 1 liter of fossil fuel. You see how these calculations show that so much of waste, the energy is wasted. It can chemical, it can be mass, it can be chemical, any form of energy you're actually not properly utilizing. Okay, so therefore, again, you can decide whether lithium ion battery technology is a green energy storage technology. Now, if you see the other problems with lithium, we import lithium from Argentina, Bolivia, and Chile. And if you go and see Bolivia, the country called Bolivia, human exploitation. You know, the governments there are so weak. The powerful countries, the socio-economically powerful countries like US, China, India, they actually live on the lithium from Bolivia because these people, the other countries don't have lithium. Maybe China has, but they still want to use lithium from Bolivia. Now we import. So if the imports are stopped for some reason, we are stuck. Okay, so we cannot go ahead. And if somebody is working with lithium salts and all that, they're actually produced outside the country. No, nothing is produced in India. And maybe some of you know, India unfortunately cannot even make its own HCl, hydrochloric acid, or sulfuric acid by its own. Okay, so many ground level problems are there. And when we are dealing with such battery technology, we are not just looking into one source, that lithium. We are also looking into other materials like cobalt and nickel, as I said. Lithium mining, huge amount of environmental effects. And what many countries advocate, they say the pollution is in Bolivia, don't worry. But Bolivia is on this planet, and pollution is not restricted. You cannot restrict pollution to Bolivia or Argentina or Chile. It's a global environment. It will have a global environment, and you have ethical issues, social impact. You're exploiting unethically the humans there, the women, the children are exploited, and then their health is affected, their natural resources are affected, and you know uh, basically you're not actually you're basically exporting the pollution somewhere else to have the so-called green energy technology in some limited countries. Okay, and you have associated materials. For example, if you want to have a EV, electric vehicle, on one hand you need a battery stack. Yes, you need lithium, you need cobalt, you need nickel, which we don't, here unfortunately doesn't have them. And then you also need permanent magnets, because these cars don't run on fuels like diesel or petrol. They run with a stator and a rotor. But how do you make these? You need permanent magnets. Again, countries like India don't have resources of permanent magnets. We have to depend on other countries. And some of you might be knowing, per car you might need at least 5 kilograms of permanent magnet. Where do we get these associated materials from? Okay, that's a big problem. And then once the batteries are there, and after 10 years they're again not working, what do we do with them? Do we have recycling technologies to recycle lithium, cobalt, nickel, and other precious metals, and then use them back in manufacturing a new battery? No. Poor recycling. That's a big lacuna or a big problem. Yeah. In not only our countries, all the developing countries, that's the same. Poor policies, mining policies are bad, human child exploitation, equality is a problem. You don't pay, and then if you see the imports, for example, in India, we spend about US dollars 1,000 million per year to import second grade lithium ion batteries. Okay, so through electric vehicles, we don't eliminate emissions, but we basically export emissions to, we think it's we're exporting to few countries because they're weak, let them suffer, but we'll have EVs in our on our roads. Okay, that's bad philosophy, because they are a part of this world. I mean, you cannot think that let them suffer with pollution and we will. It's not. At some point of time, it becomes a cascading effect, and then the pollution is a global phenomenon. Okay, so this is okay. This is with regards to the lithium battery tech. Now let's see the third example, which probably many of you have encountered: green hydrogen technology. This is basically comes under the transportation. but I'm pretty sure many of you know we have been producing hydrogen for such a long time from fossil fuels. Okay, 90% even now throughout the world of the hydrogen is produced from fossil fuels. Just a minute now. Now, once you use fossil fuels, it is called as a gray hydrogen. I hope some of you know that there is something called gray hydrogen, blue hydrogen, and then comes the green hydrogen. Then what is blue hydrogen? Some of the companies, some of the research institutions, just to promote their work, they produce hydrogen by using non-renewable energy sources, and that hydrogen is called as blue hydrogen. Okay, yes, in the case of blue hydrogen, still there is a large carbon footprint, but not as high as that in the case of gray hydrogen. Now, because of the poor policies, many companies actually are promoting blue hydrogen because getting green hydrogen, when we talk about hydrogen, huge amount of hydrogen is required. Okay, that's why I use the word humongous amount of green hydrogen. And unfortunately, throughout the world, there is no mature technology that can actually give huge, such humongous amount of green hydrogen. Green hydrogen means it is clean, renewable sources are involved, and very minimal effect on the environment. As of now, there is nothing like green hydrogen. It is only blue hydrogen. But the if you see the life cycle of the blue hydrogen too, there is still carbon footprint, but luckily there are technologies where you can capture the carbon and then reuse in some other system. That way blue hydrogen is acceptable, but green hydrogen, of course, why many are not promoting or not investing is because this can be disruptive and investment already made producing gray hydrogen, blue hydrogen may be wasted. Okay, so that is why you can see throughout the world now India started rolling out DST, for example, is rolling out advertisements for developing system level electrolyzer, 5 kilowatt, 10 kilowatt, whatever it is possible, system level electrolyzers, Indian made electrolyzers, because in electrolyzers you all catalyst, and catalyst means these are all mostly highly active highly active catalysts are platinum, ruthenium. These are very costly and not available. Okay. Now, and also there is a demand supply relation is pretty poor. Do we really need green hydrogen at this point of time or in the immediate future? That is also not very clear. But still, because it is very interesting and this is buzzword. Many people say I'm working on green hydrogen production. Some people say I'm working on green hydrogen storage. But if you really check what they're doing, it's actually not even blue actually, because in doing their research, in conducting what they're doing, somewhere the fossil fuels are used. The moment fossil fuels are used, there are green gas or greenhouse gas emissions. Therefore, you can only there is a hand. I saw a hand.
No, think.
Yeah. Okay. Okay. So, system level electrolyzer research is extremely poor, not only in our country, but electrolyzer is an electrochemical system where hydrogen is generated. Okay, many people actually think that the fuel cells uh, uh, generate hydrogen, but it's actually hydrogen generated from the electrolyzer goes into the fuel cell. Okay, so they're both different. Okay, for this, I'm considering electrolyzer. Electrolyzer is an electrochemical system which actually produces hydrogen. Okay, and then transport and storage facilities. How do you transport? Can we use the existing pipelines which should transport the fossil fuels and other oils for transporting hydrogen? Do we have storage facilities to store hydrogen? Because hydrogen embrittlement is such a big problem, a big material science, materials engineering problem. Okay, so these are all the problems related to uh, green hydrogen technology. But as of now, as of now, and as far as my knowledge is concerned, as far as I am concerned, there is nothing like green hydrogen technology, because nowhere in the world with a minimal effect on the environment, hydrogen is produced on a bulk scale. Now, what are the other problems? Poor understanding on the overall scenario. Okay, most of us, what we are interested in to do some research, to write some papers, academicians mostly, and some of them want to promote their work. Some of them go to the industry in order to sell their product. You hide certain things. Okay, so poor understanding on the overall scenario. We are only interested in business, but not in real environmental production. Poor academic and research training. We don't get training academically in the classroom or in the research. There are so many such problems. One of them is research reporting. In most of the times is high overstated. Okay, we don't even know why we are using green. We think that if we use that nomenclature, our work will go through. Okay, but if you do a mistake at this stage, at a primary basic research or applied research, it becomes very difficult to translate that into a product. Many people don't realize that, but still they, wherever they get an opportunity, they say, mine is a green chemistry, mine is a green product, mine is green technology. But, if somebody takes it up, let's say, and wants to translate into a product, then it becomes problem, because if you do some quantitative sustainability calculation, if you use the sustainability descriptors, it turns out to be a nonsense technology. It's not useful. Okay, and not many work on allied green energy technology. There are several other green energy technologies. If you remember, I showed you one slide where energy conversion technologies are there, energy storage technologies that are there, energy transportation technologies are there, but there are several allied green energy technology. For example, inverter. Um, uh, we don't work with electrical engineers or for example, somebody is working on let's say solar electrical energy conversion. Okay, but because it's an intermittent conversion, intermittent technology, you need storage, and then you need but when you convert solar to electrical, it's DC, you cannot use it, so you need to convert the DC to AC. Therefore you need an allied green energy technology, which is a green inverter. Okay, so which efficiently converts DC to AC, but we don't work. And when we do conduct research on green energy technology, we don't even consider the grid parity, whether my work will be helpful in connecting to the grid. We don't do that. Okay, not many do that. Okay, so these are all the problems. But then what is the way out? Are there any recommendations? Are there any uh, solutions, possible solutions? Let's see one by one. Okay, so some key recommendations. I'll go one by one. Okay, the first and foremost, as far as our academics, or somebody is working in a college or a university is inculcating good research practices. What is good research practice? Research cannot be arbitrary. It has to be based on design. A single experiment, it cannot be. We often use a trial and error. Trial and an engineer, a scientist cannot use the words trial and error. There's nothing like trial and error. Any research has to be based on design. Even hypothesis has to be design based. Okay, so we have to inculcate the youngsters, and we also have to do our research based on design. What most of us do, we look into the literature and we take up a hot area and do some incremental delta X, and then our motive is to publish and show those publications and get a promotion. Okay, so but there ends the matter. Okay, but in that way we actually waste a lot of resources, and then our we end up doing nothing actually, because that's not useful to the society. And reporting the reality is something which actually is very much not there in many of the countries. Because of the peer pressure, we always want a quick publication or a quick patent or something like that. We hide several things. If you use let's say sustainable descriptors as simple as for example mass and energy balance calculation. I'm not saying about complicated calculations, just the first approximate mass and energy balance calculations in doing whatever it can be materials related, it can be processing related, it can be fabrication, it can be usage, whatever it is. If we have a first approximation mass and energy balance calculation, if the calculations tell you that your process or your fabrication process or your product is not really green, please report that it is not green. Okay, but we don't. If even if you see the PhD and MTech or BTech theses, none of them will have a negative result. Somehow every book will have only positive result, and it is unimaginable that something how without facing any failure, how you are getting success, and more so even if the work is not design based. Okay, if it is a design based, maybe the failure percentage is less, but otherwise it is impossible. Okay, so reporting the reality, and we should encourage mass and energy balance calculation at least the first at the academic level, at the masters or the BTech or at the PhD level. And we should encourage let's say something called scorecard based reporting at the sustainability aspects. We should identify the sustainability descriptors, in terms of mass or energy or whatever it is, and then ask the on we also should calculate when we do some work. Some quantitative analysis has to be done, and then we should consciously link our work to the SDGs. Okay, this constitutes, in my opinion, a very good research practice. And when it comes to processing, you should, some of you might be from chemical engineering. You will appreciate that flow reactor type and how high throughput processing has to be encouraged. Not milligram scale or microgram scale. We should see that our process, what we are developing to produce a particular material or a compound can be done at a large scale, and flow reactor type means any byproducts are again captured and reused in the process. Okay, something like that. That should be from the beginning. We should encourage now. It's high time that we should go to the next level. And alternative chemical assessments, accelerated materials development. See, India, it depends on materials. Where do you get the materials from the nature? And nature itself has decided that at some places lithium will be there, at some places tungsten will be there, at some places some other material. So we cannot alter that. We cannot say, or otherwise we have to occupy, some other place by force and say, henceforth this land, right? So depending on the availability, local availability of the materials, is there a possibility? Is there a possibility? Can I, in some many materials, hafnium is used, for example, but we don't have hafnium availability. Nobody will give hafnium. Then can we replace hafnium with something? Can we replace tungsten with something else? Okay, but that should be an accelerated development, materials replacement. For that, you need to incorporate artificial intelligence, machine learning, and something like that to quickly do such. And of course, now you might have also heard about startups coming in solar energy, startups coming in space. We should be encouraged to get a ranking. Please show that your technologies are developed based on some sustainability parameters. Please, then only we will allow you to continue. Okay, and then make technologies like RRR technologies, reuse, reduce, those technologies an integral part of research. You should encourage the students. We should encourage the students. Okay, and then of course we should, when there is a developed technology, we should bring out more efficiency out of the, can be conversion efficiency. In the case of solar energy, for example, we should always work on one hand the sustainability aspect, on the other hand the efficiency. The moment efficiency increases, obviously the emissions and other related things will come. Okay, these are one set of recommendations. Manufacturers, the one on the academic side, one for the manufacturers. There is an industry, including the mining industries. Okay, mining industries are the ones which have to do very responsible mining. Okay, for them, it's not the profit, it's not about the fame, it should be the environment first. Okay, the irresponsible mining actually causes a lot of detrimental effects in the environment. So manufacturers should also, if the company is there, they should actually get some ranking based on some sustainable balance. What we are doing is a sustainable thing. We are not, the environmental impact on mining something is minimal. This is how we have calculated. Please rank us. They go to the third party and get the ranking done. Okay. And then integration is a big problem. I have lithium ion battery technology. I have solar conversion technology. And then, but unfortunately, the integration between the two is not. I have a technology, but the technology is not, doesn't have a grid parity. Cannot be combined with the existing grids or smart microgrids or a grid development. No, it is a technology which is a technology, that's all, but it cannot be integrated into. Such sort of things have to be avoided. If there is an idea, we should actually integrate two so-called green technologies to make it more greener. Okay? And more investments in mature technologies and allied green technology. This is especially for those industries which have a lot of money, but they invest in, they have already these, the techno. Sometimes the technologies at some point of time are technologies, but once they become richer, they they uh, they, they they are not in line with what is happening. They're only looking for profits. Okay. Now, such people have to be told that please invest in mature technologies. Your profit is not important. It is the environment that is important. Okay. So such things have to be encouraged. Wherever there is an opportunity, we should encourage such things. And as I said, disruptive technologies. If somebody has a disruptive technology, we should encourage. We should not say that, well, the old technologies, it will be wasted and all. But instead, in fact, if we have disruptive technologies, a huge change, for example, blue versus green. Imagine we have a really green hydrogen technology. Okay. And in all respects, storage, production, storage, usage, everything is green, then half of our problems related to environment will be solved. Okay, and then the sustainability levels actually of life on the planet actually increase. Okay, but it can be through a disruptive technology. But the manufacturers or the industrialists actually should promote if there is a disruptive technology. They should not suppress disruptive technologies. Okay, and of course, the policies are very important. Regulations and policies are very important. For example, in some of the countries, European countries, they introduce the recycling first. They only introduce the technology later. For example, lithium-ion battery. Only when they are sure that everything from a wasted lithium-ion battery can be recycled. Only when the technology is matured, they will introduce the lithium-ion battery technology in the market. Otherwise, they do. So that has to be done, very carefully. And of course, the culture and public awareness is so poor that we also carry forward some wrong information without verifying. Therefore, it is very important to have awareness programs so that we are not cheated. Somebody can sell us a solar cell, solar panel, saying that it's so efficient, you can use it in your home and all that. You should be careful because we don't know. We should look into how much of pollution that was created in manufacturing that solars. Okay, and we should see if any technology has human exploitation. All that we have to take. I think with that, I thank you so much for listening, and we can have a question and answer session. I'll be happy to answer your questions.
Dear participants, if anyone, I'm enabling the chat box as well as the
There's one hand. Where do I see the questions? Chat.
Yeah, I'm going to enable just now. Just
Okay.
Nagras, you can.
Thank you, sir. Sir, my doubt is actually currently we are delivering lectures on waste to energy to the all the engineering students irrespective of stream. So we are introducing, of course, one case study as a part of evolution. In that, we are one of the topic is hydrogen is the next generation fuel from biomass.
Yes.
The thing is, topic looks good, but in the research point of view, where can we start the production of hydrogen from biomass? Like, is it possible
So
through
basically,
any?
yeah.
Yeah, please, sir.
I think I lost you. I think you're muted now. Is your question
Sir,
over?
question is over, sir. Actually, research point of view, where can we start
Yeah.
these studies?
So
Is it?
basically, it starts with, as I said, design based. So what is meant by design based? Okay, the choice of the screening of the biomass itself. So where do you start if you say biomass? Let's say hydrogen production. Okay, what is a biomass? How do I choose my biomass? Okay, that is where you should start. The screening of biomass, there are protocols in screening biomass for different aspects. If I want, let's say, porous carbon, okay, if I want carbon, if I want hard carbon, if I want oil, if I want something else, there are protocols too, well established. We don't need to newly develop a protocol. Okay, so when mass to energy conversion, mass to mass conversion, you know, first thing is the screening of the biomass, depending on what is required at the end. Okay, that is one aspect. The other aspect is the process. It can be a single process, it can be multiple processes. And when you want to introduce a process, you need to incorporate quantitative descriptors related to the mass balance and energy balance. Even before doing the conversion, even before conducting the experiments, you need to theoretically calculate, thermodynamically calculate how much of energy is needed, how much of mass is needed, what is the conversion efficiency. All such aspects have to be thoroughly theoretically, because on paper, on theoretically, you're not expending any consumables, you're not expending any energy, you're not doing anything, you're not wasting anything except for your energy while calculating it. So the student should be told that you should incorporate, first figure out, first screen appropriate, maybe multiple biomasses, and then the choice of the process. And when you do that calculations, and then, as I said, flow reactor, and then only when everything okay, it seems to be all right, then you conduct the experiment. Okay, and then, as you said, conversion of biomass to hydrogen is something close to a dream. It is not to speak, to tell, to talk, give a presentation, it is nice, but you know conducting an experiment in a lab. Let's say you are conducting an experiment, hydrogen is produced. What would you do with that hydrogen? Would you send it into a fuel cell? Would you leave it in the lab? Or would you leave it to the environment? Is it only hydrogen or some oxygen is there? So all of this not only needs design but also a careful control, safety, for example. It is hydrogen can be disastrous if it is associated with some pressure. It can be like a bomb. Yeah. So safety consideration, all such things, uh, we have to make our own calculations and then tell the students. But what we do is we pick up some textbooks which don't give these calculations. Basically, none of the textbooks actually look into this. They only qualitatively describe this is or the work done is already put in the so-called textbook. But we don't want to replicate that work. Don't want to repeat the work that is already done by somebody, right? For that, it has to be based on design. So I conclude. I mean, that you have to look into the design aspects of anything related to even related to the energy technologies. Okay, so quantitatively, you have to design the reactor. You have to design the reactor. What we do, we'll look into how hydrogen is produced by somebody else somewhere else, which is published. We also want to buy that by through a project. Okay, such things should not be inculcated to the students. Am I clear?
Yes, sir. Actually, I agree because when students are trying to submit case study report, they are looking into various internet sources and they are
Yeah,
preparing. That's fine. But by looking into the report, yeah, it's very good. Someone has already done some work in
done.
biomass. They produced
Yeah,
hydrogen. They are claiming this is the
yeah.
efficiency, blah blah, but something else. But when it's come to my point, where can we start, like establishing design experiments in the lab or conducting some simulation studies?
I
Um,
think you should start with the
that's
simulation.
where,
You should start with the modeling and simulation, some calculations, some thermodynamics, some at a different level, some at the atomistic level, depending on your expertise. But don't jump into the experiment directly. That's my recommendation. Do not jump into the, and we should also carefully assess whether something reported is correct or not. Yeah, that's very important. Assessment of
yes,
the literature. What we do, we assume that whatever is reported, whatever is published is correct, but it need not be. So we
yes,
should also have our expertise developed to assess what is published, right? That we should make sure that what is published is correct.
yes, sir. Yes. Thank you, sir.
Yeah.
Any other participants, please?
Sir, I have a small query, sir.
Yes,
So,
please.
what about solar PV recycling strategies, sir? So, like that, is it feasible option for doing that recycling of solar PV panels?
Yeah. So, see, firstly, we maybe only recently we started making our silicon. Okay. Otherwise, we have been importing these silicon wafers and or panels themselves from outside. Okay. Now we don't know because of the mutual agreements and all. We cannot actually do the reverse engineering. We are prohibited to do reverse engineering, and so we don't know really what is the dopant in the silicon, what sort of silicon is there. We are afraid to do reverse engineering. We don't do that because it is against our ethical philosophy. So, but don't we know already silicon technology, both processing silicon from silica, sands, and we know that. Okay, but somehow we are lost in the race, and we are maybe 100 years delayed in that. Now, once the panels are there, okay, the government is now having different policies to collect this waste, and they are not sure whether everybody can do it because a lot of metallurgy is involved. And when metallurgy is involved, safety is also involved. And when you have toxic chemicals used to prepare something like that, and when you want to reprocess it to collect the silicon, lot of toxic chemicals which are there in the circuits may come out. Okay, so on one hand, it is very interesting, but I don't think anybody started in a big way. And for that to do, your lab has to have some safety standards. You cannot do such metallurgical things, especially when I have a wasted solar panel. I cannot just melt it in open air. It is not like that. So uh, a lot of things are there. Yes, it is doable. It is done previously, but it has to be done in a controlled environment. It is not that I can do it in any lab. That is the problem.
Sir, one more thing, sir. How long it will degrade in the soil, sir? This solar PV panel. Suppose we are going to dump in somewhere. So
So we don't
plastic
dump.
handle it
We
take
don't.
years of time. So similarly,
Yeah,
how much? Yes, sir.
yeah. So see, landfill, the degradation of such such things in landfill is not considered at all. See, they can stay they degrade or not degrade doesn't matter. But so much of pollution is already generated in producing them. Why to dump them in the dump them as a landfill, right? The
Okay, sir.
option of filling the land with such materials is not there at all. You should not even consider that.
Okay,
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 see,
sir.
it has to be it to have a circular chemistry or circular process where once they stop working, you collect them and take them to a place. You reprocess them, you get all the elements back, and then you reuse them in making new panels. Yeah.
Sir, as you said,
Uh,
is life cycle assessment is needed for each and every
Very,
clean
very much,
technology.
very much. In fact, in mechanical engineering, in chemical engineering, and environmental engineering, energy engineering, which Subbu is done his MTech, life cycle, very proper, very quantitative life cycle analysis should be there in every semester in the last few semesters. I mean, of a BTech or in a tech. Life cycle analysis one, life cycle analysis two, something like that, because it's so important now. In order, even before doing anything, you have to do a complete life cycle analysis for any technology.
Okay, sir.
I think I have some questions on the chart. I feel theories developed well, but to reach in Indian public, can we develop cheap technologies that can be implemented to prevent? Yeah. See, first thing is the environmental. We don't need to look into whether something is cheap or not, because government has so much of exchequer. If they are able to spend dollars thousand million per year to import batteries, cheap technologies are not needed at the first place. At the first place, local technologies are needed. I use local materials. I use local technologies developed by us, patented by us, and then why is it important? Because of the resource problem. If we use local materials, there is no we don't need to depend on other countries or other places for resources. Okay, that way, for example, uh, I would recommend, let's say, aluminum ion batteries or sodium ion batteries for India. Why? Because we know aluminum chemistry, we know sodium chemistry, we have lots of aluminum resources, lots of sodium resources. We know metallurgy of aluminum, we know how to deal with the dross, we know how to deal with the wasted sodium. Yes, their efficiency is much less than lithium ion battery. Maybe they are a little costlier now than lithium ion battery. But when it comes to sustainability for India, it is always aluminum, and they let them not work as efficient as lithium ion battery. But the amount of money we spend on lithium, because we have to import everything for lithium ion battery. We don't produce anything in India for lithium ion battery. Even somebody says I made a cathode material, the lithium in the cathode material has to be imported from somewhere. Okay, that way it becomes very costly. Okay, something like that. So cheap technologies come later. First thing is local technologies which can be sustained with the local resources. That is more important. Then over the time, as the technology matures, the cost can come in. Yeah, otherwise governments normally bear such things. They are not on the public action. Yeah, there is another. I hope I've answered your question, Shanmuka. Huh?
Sir,
Okay,
please.
sir. Yeah. Can we exploit solar thermal fluids to propose green? Yes. So, solar. Say, I'll tell you something very interesting. most of us know that no solar photovoltaics. But if you see the different solar energy technologies, the most efficient solar energy technology is solar thermal, where these fluids are involved. Okay, and fortunately, India and Indian government and many of the companies are now uh, uh, exploiting these fluids for and also the building materials, basically coating technologies. They want to actually make self sufficient building materials that can actually absorb solar energy, and maybe in the pipes where solar these fluids are there, and then internally they are heated up and the heat energy is converted into electrical energy. Yes, that actually government and many institutes are working on such ideas. Yeah. Then
Hello, sir.
what is that? There is one more.
Naresh,
Yes, please. Yeah.
Sir, good evening, sir. This is Dr.
Yeah.
R. Naresh.
Yeah.
Sir, I got one query. You mentioned when we are going through literature review, so we need to filter the
Mhm.
literature. Can you give
Yes.
some suggestions or what is the way we need to look at that?
Yeah. So, uh, so I teach a course called research methodology. Okay. In
Yeah.
that, I teach a method called iteration method. You can look into, you may not know that. You may look into the internet and find out there's something called iteration method. Okay.
Okay.
Iteration method to read literature. Okay,
Oh,
it has
okay.
three iterations: iteration one, iteration two, iteration three. In iteration one, you there are some tasks. In iteration two, there are some tasks, and iteration three, there are some tasks. Okay, once you do this iteration method on a set of literature you have collected on based on some keywords which you are interested in, the,
Okay.
this method actually, this is one actually the best method, I would say, to actually filter the literature, get whatever you want, and see the best one. That means a reliable one. Okay, so please get to this iteration method of reading literature. It's
Sure,
very
sure, sir.
interesting. Yeah,
Sir,
that
one
that
more
will
thing, sir.
help you. Yeah,
Yeah, you mentioned
yes, please.
we need to do simulation studies before doing experimentation. Kind of research, or it is going to keep changing from topic to
No,
topic?
it has to be. No, it has to be. I mean, by nature, it is like that, right? You don't want to waste resources. You don't want to waste your time. Then how do you do that? So, for
Mm,
example, a processing technology is there. The first thing is materials are involved. Then,
yes.
when materials are involved, some temperature is involved, some pressure is involved, specific materials are involved, specific compounds are involved. What do? I go to thermodynamics and ask thermodynamics, please give me the best way to deal the reaction between these at this temperature or this range of temperatures or these range of pressures, right? Gives
Mhm.
free energy
Yes.
minimization. Yeah, we do that.
Yes.
That's a
Yes.
natural thing. So it has to be. Nowadays, the computers are so powerful. The algorithms are so powerful. It's so easy. Anybody can actually user friendly algorithms are there. Only thing is we need to have an idea. That's all. Okay. Then you
Okay.
do the simple modeling and then simulate, and then okay, among all the ideas that are the outcomes of running the algorithm, you pick the ones which you can do in your lab and then conduct the experiments. Right? That's the
Yes.
ideal way. That's the ideal way.
Yes, sir. Actually, I work in thermal energy storage using phase change material. Do you
Okay.
suggest any kind of tool which will be very much suitable, which will be
For
giving good
phase change
results?
materials, yeah.
Yes.
Basically these are all organic salts, I suppose, organic
Fatty
materials.
acids, actually. Fatty acids
Fatty
and some.
acids, basically. Yeah. Fatty acids. Basically, thermodynamic stability. Basically, you have to study because you want high thermal conductivity, but they should not melt. That's what I
Yes.
suppose,
Yes.
right? Yeah.
Yes. Yes.
So yeah. I think simple thermodynamic softwares, FactSage, thermocalc. These can be used, but you have to have appropriate databases because numerous databases will be there. For fatty
Hmm.
acids, there must be a database, and then you know which is environmentally friendly. Then all the thermochemical data you should have in the database. Then the algorithm will collect the thermodynamic data and tell you the stability, right?
Okay, okay. So
Yeah.
thermocal and one more tools. Which one? Which is the tool?
Thermocalc, FactSage.
And fact siege.
FactSage, FACTSAGE.
Oh, okay, sir. Okay. These are
But
the
these
two
are basic.
open
These
source
are not
or
open. These are no. These are commercial ones. But they
okay,
can tune depending on your requirements. Okay, because they are all databases of these have to be stronger. Algorithm is
okay,
all right. Algorithm is mostly the same, but it is the
okay,
databases that matter. Okay, so you
okay.
have
In
to
that,
look
all the
into.
materials database is there. You see.
Yeah. Various databases are there for metals, their steels, their alloys,
Hmm.
like that. You should
Hmm.
have a fatty acids database. Otherwise,
Okay,
you can also generate the database using the data tables and then ask them to incorporate in the software. So they can customize the tool for you, actually.
okay. Sir, last one more query. You mentioned
Yes.
very much important to perform life cycle analysis for any study
Mhm.
before study. Can
Yeah.
you give some suggestions of any tool like which can help us to do life cycle analysis, especially like open source, so that everyone can comfortably do that?
Yeah. I think, I mean, I don't remember, but maybe Subbu might have an idea. Maybe I'll go through. I have somewhere the material. Maybe I'll
Okay.
pass it on to Subbu. Yes, there are available. In fact, nowadays, most of the textbooks related to this, they have different models depending on the type of work. You can actually
Okay.
pick up a model and do a life cycle assessment. Yeah, with respect to energy or mass or combined. There are several models now. Huh?
Okay. Okay.
Yeah.
Nice,
Sir,
sir. Nice.
Right.
sir,
Thank you, sir.
Yeah. Thank you.
hello. Yeah,
Yes.
sir, in one of your slides, you told that 300 liters of fossil fuel get burns for the
Mhm.
generation of means the lithium and battery. It is equivalent to 1 liter of petrol or diesel. So my question
Yeah.
is
Yeah.
whether we should adopt these technologies, battery technologies, or not.
See, there are multiple aspects in this. One is, in true spirit, we should make it truly green, which is impossible. Okay. Why? Because if you want lithium, you have to mine lithium resources, right? That is highly polluting. And if you want to mine 1 kilogram of lithium, not lithium source, that means it is in some compound form or some ore form, 1 kilogram of it, you have to use 20 lakh liters of water. Okay, so that itself shows it is not good. Okay, but there is no harm in looking for alternatives. That is what we are doing. Okay, but from my perspective, I will not pollute Bolivia. I will not harm the people of Bolivia. I will not violate the human rights of people in Congo and Bolivia to get my lithium ion battery. That's the philosophy. There are many European countries, they said, we'll have our own technologies, but we don't want lithium ion technology, like Finland and Sweden. They said no. Why? Because it's a violation of human rights. That's the philosophy there. Okay. So if that's one part, but you know, there is trade. For example, why India is buying so many batteries from outside? If we don't buy, the other countries won't buy our products. Let's say our rice or some other. So there is a trade problem. Okay. So there are multiple things associated. It's not purely technology. Okay. There are business aspects, there are socio-economic aspects, there are political aspects, there is lobbying aspect. Okay, apart from the technology. Therefore, now if you see the government of India has changed its, they are saying beyond lithium ion battery. They realize that we cannot sustain lithium ion battery technologies in India after some time. Therefore, they are asking, if you see the recent calls for proposals, they are saying beyond lithium ion battery technology. Using materials, let them not be as efficient as lithium ion batteries, no problem. But within India. Raw materials from within India, everything within India, technology from within India. Okay. So as we look for alternatives, till then we can probably use, because once they start working, definitely there is a positive aspect. The pollution comes down when you have EVs in comparison to the car or the automobiles run on petrol and diesel. Obviously, the EVs, once they start working, if you don't consider the way they are produced or the pollution that is generated when they are produced, from that part onwards, they're okay. Okay. But as we use, we should also develop other alternatives. That's what I can say.
I think
Yeah, there's some questions also on the chat. Battery and supercapacitor storage using natural materials like bamboo or natural feasibility and viability. Yeah, basically supercaps are limited by the type of the electrolyte. Its supercap is not limited by the electrodes. Okay. If you see the basic equation half CV square, the capacitance of a capacitive material, we most of the researchers are worried about the C, which is material dependent. But you have a V square, what is the voltage? Okay. So that is electrolyte dependent. If you have aqueous electrolytes, you are limited because they get disintegrated beyond a certain voltage. Okay. So in practice, why we don't have supercaps in market? That is because the open circuit voltage is so less. Okay. Therefore, they are not really in the market. They are not so useful. If you use non-aqueous, maybe the voltage range can increase. That V square will be very good, no problem. But the problem is the safety, and the problem is the availability. So converting bamboo or natural materials which can be useful as a carbon material is not a big thing. Many carbon forms have been developed. That is not a big issue. But issue is with the electrolyte in the case of supercaps. So if you can develop an efficient electrolyte that doesn't disintegrate beyond 4 volts or something like that, and still aqueous, that can be very good. Okay. Yeah. What about the ocean usage in India? Some countries are using. Yeah. Yes, we can also use that energy, but the efficiency is quite low, and the transmission is a little difficult. In between, the losses are also yes. Of course, when I say that, in fact, for countries like India, we cannot rely only on renewable energy technologies. Okay, the requirement is so high, the know-how, the awareness is so bad. We don't even switch off our lights and fans when we leave a room. And lot of theft is there in the transmission. Okay, lot of losses are there because the lines are not properly done. So in such a scenario, we cannot think of relying or meeting the requirements, the energy requirements, especially in India, with only renewable. That is why if you see, government of India on one hand is encouraging the green energy technology, on the other hand, it is also encouraging fusion program. Why fusion program? Very efficient, very clean, no, not so much of waste, nuclear waste, in comparison to the fission. The only apprehension is it can be dangerous. Anything can be dangerous. Hydrogen can be dangerous. If you don't drive your car properly or rashly, it is dangerous. If you don't operate your cylinder properly, if you abuse the cylinder, it can also be dangerous. Okay, so it goes by the philosophy, it goes by the technology available, it goes by the interest, it goes by the the want of a country. So therefore, if you see, they are very good in fusion. Maybe soon these fusion technologies will come, and our energy required, because the mass required is so less. The it's a clean form of energy. It's green, no emissions. The only problem is whether it is safe or not. Okay, grid parity, the existing things can be used. We a lot of power that comes into our households is also from nuclear, from in addition to the other non-renewable sources. Yeah.
I
Yes.
hope everything is clear from our audience side.
I hope Ravi can continue.
Okay, sir. Thank you so much, sir. Your expertise and in-depth knowledge shed valuable light on sustainable energy solutions, inspiring us all to explore innovative approach in this critical field. Your ability to connect theoretical insights with practical applications left a lasting impact on the participants, encouraging us to think critically about our role in fostering a greener future. The strategies and ideas you shared will undoubtedly enhance our teaching and research endeavors. Thank you once again for your time, dedication, and invaluable contribution to the session, sir. We look forward to future opportunities for collaborations. Thank you so much, sir.
Wonderful. Thank you so much for giving this opportunity. I hope I have not bored you. Uh, I speak like this. So uh, Subbu knows for quite some time. Uh, I hope I could convey at least 50% of what I wanted to convey. And I'm again sorry for changing the topic. I could also
Welcome.
No, sir. We
uh,
actually the session was really informative, sir. We liked it all.
I hope so. Yeah.
Good. Thank you so much, and it's
Thank you.
very really informative, and we covered almost all aspects related to the ground level problems as well as sustainable goals, how we have to achieve those goals, the recommendations for that. I think everyone we have to rethink about those things, how we can maybe
Yeah.
how to reach those goals. That's very important for us, and it's really very informative, and I think for everyone, I think really like us this. So thank you so much once again for accepting our invitation, even your busy schedule. So thank you so much.
That's all right. Yeah. Thank you. Thank you for giving me this opportunity to interact with so many in one go. Let's see if we can meet again and do something else.
Yes.
Thank you.
Okay. Yeah. Thank you. Thank you. I'm logging off then.
Okay. Thank you.
Okay.
Now, Ravi, could you please proceed to the next session?
Okay, sir. Okay. So, good evening, everyone. It is my distinct honor and privilege to introduce our esteemed guest, Dr. Sarvottam Jyoti, sir, who will be addressing us during today's faculty development program. Dr. Sarvottam Jyoti, sir, is an associate professor in the Department of Mechanical Engineering at the prestigious National Institute of Technology, Calicut, Kerala. With expertise spanning jet flows, aeroacoustics, aerodynamics, and combustion, Dr. Sarvottam Jyoti sir has made remarkable contribution to research and academia. His journey of excellence began with earning a PhD from IIT Madras, where his work set a strong foundation for his career. This was followed by postdoctoral research at the Korean Advanced Institute of Science and Technology, South Korea, where he had dwelled deeper into the cutting-edge studies on shock-associated noise. Dr. Sarvottam Jyoti sir academic endeavors have been richly acknowledged. He is a recipient of Young Researcher Award by Institute of Engineers, along with prestigious fellowships from renowned organizations such as Indian National Science Academy. His ability to balance rigorous research with active membership is evident from multiple PhD and master students he has successfully guided, fostering a new generation of thinkers and innovators. Beyond his research, Dr. Sarvottam Jyoti sir is deeply committed to fostering collaboration and knowledge sharing. He has been instrumental in organizing various workshops, conferences, and professional development programs, ensuring the determination of advanced knowledge to future engineers. Dr. Sarvottam Jyoti sir affiliations with professional societies such as Aeronautical Society of India. As a passionate educator, he has inspired countless students through his engaging courses on fluid mechanics, thermodynamics, heat transfer, and aerodynamics. We are indeed privileged to have such a luminary with us today. Dr. Sarvottam Jyoti sir, insights and expertise promises to be enlightening and transformative for us all. Please join me in the welcoming Dr. Sarvottam Jyoti sir to this session.
Yeah, thank you, Dr. Ravi. Thank you. Is it audible?
Yes, sir.
Audible.
Okay. Yeah, just a minute. I think video is also visible, right?
Yes.
Okay. Maybe for a short duration, I'll keep my video on, and later I'll switch it off based on the bandwidth. Okay. So let me share my slides. Dr. Subramanian, is it visible?
Yes, visible. Keep it in
Clear,
the
right?
flight mode.
Okay. Okay, so very good evening to all the participants of this FDP program. So I understand that the FDP is on innovative green energy generation and storage technologies by Dr. Shiva. However, I thought I could slightly deviate from the topic, and I would take a slightly different topic, which is on the design and innovations in energy systems. Okay, so I'll go with the table of contents as follows. First of all, I would like to give something about why we have to go with this design and innovations, and why it is important in the present conditions. So you can see that in India as well as abroad, the concept of startups are getting more wider reach. Because a lot of new technologies are coming up, a lot of new ideas are coming up, a lot of new inventions are coming up. Now, mostly that inventions has to be converted to some commercial aspect. So in order to convert to some commercial aspect, we have to undergo certain features for that, right? So whatever we design and develop will not go into the commercial aspect. Only a certain which are useful to the market, which are very much useful to the society. Okay, the products which are useful to the end usage, only such products will will be commercialized. Otherwise, they lag in some areas, and it cannot go as a commercialization of that product. So it is applicable to all. Either it can be a renewable energy source, or it can be any source as such. Okay, any product or any service as such. So we have to follow a certain procedure or stages, okay, if we want to become successful in the market, either in terms of a renewable energy source or any other source. So in that way, I thought I will deliver the talk with this table of content. Okay, so the motivation, innovation, the types of innovation, the design thinking, and stages of design thinking, and how it can be applicable to the renewable energy systems. Okay. See now, innovation, as said by the famous industrialist Steve Jobs, is the ability to see the change as an opportunity and not the threat. Okay, so because daily a lot of changes are happening in the market, a lot of changes are happening in the world. Okay, so power plants are going off, and PV panels are coming up, and the wind turbines are coming up. So we should not see such thing as a threat to the society. Okay, so it is indeed good in some way. So as human has grown up, the innovation has also grown up, starting from the ages of the wheels. Okay, the human has grown up to this stage. So innovation is a must to the mankind, for the mankind to grow. And innovation requires deviations from the conventional way of thinking and doing things, right? So that is obvious, because we cannot go on doing the same thing again and again. We cannot now see the fossil fuels are all consumed up. So now we have to go with some other new technologies to sustain ourselves, right? So innovation has to be there. We have to find some ways of resources for the mankind to sustain, for the energy requirements, and other usage. So innovations help in survive and prosper in this competitive world. Okay, so this the innovation has helped us to become cultivators, civilizations, travelers, place explorers, etc. So here the keyword is innovation. Okay, innovation is the keyword. So there are a lot of startups coming up with this word innovation, and many will get confused with the invention and innovation. Okay, so both are not the same. So invention is nothing but is the first occurrence of the idea. Okay, so suppose say you have got some idea that you can proceed further, maybe in terms of renewable resource or a new resource of for the power, harnessing the power energy. Okay, so that can become the innovation, that can become the invention, but still it is in the preliminary stage. Okay, that invention is in the preliminary stage, so still it has a long way to go. Many people have ideas now, many people have inventions, many people have a lot of ideas, but all the ideas cannot become innovation, or all cannot pursue that idea to become an innovation. Okay, so invention can happen anywhere, in universities, or whenever we are doing some free thinking, or in the research lab. Okay, making some new design products. Okay, we'll get an idea about the invention. But innovation is the commercialization. Okay, so once we come into a commercial sphere, okay, see, startup is nothing but a commercialization, right? Whatever we plan to do, or whatever we idea that we develop, it has to be made into a money for the business to run and world to sustain. So in that way, the first commercialization of the idea becomes the innovation, and that revolves around the commercial sphere. So there are a lot of it takes a lot of time for converting the proper or a new idea to the innovation stage. Okay, so some examples that we can give are something like this. Although the COVID vaccine was invented well in advance, but it took a very long time to come into the market scale, right? Same way, see, any idea can be invented in advance, like the PV solar PV panels or wind turbines. Okay, the idea will be invented, idea will be there, but getting it into the usable aspect, okay, at the stage of usage where the customers has to use, okay, in that case it will take a very long time. Okay, so similarly, other example is the online transactions. When online transactions were invented, it took long time because some technologies will take a long time to adopt. Okay, same, I can give you the same example with PV panels, right? Still, although we say that PV panels has come into the large scale, but still in the household, many have not started to use it. Right, so the penetration of this new technologies will take a very long time, okay, compared to the conventional technologies. So the idea is the first occurrence of the idea to become into the innovation aspect where the commercialization involves will take a very long duration of time. So whatever you are generating, okay, whatever you are developing, whatever ideas that you are trying to do and make it as a innovative product, it should converge to this point, okay, it should converge to this spot. So there is a desirability or why such a product has to be existing to be done, okay, so that is the desirability and viability of the product. Okay, so how it can be utilized by the people, how much cost it will be, whether it will be used by the consumers or not. Okay, and the feasibility, whether such a product can be made or not. Okay, so all this should converge to a very neat spot here. Okay, then only the whatever innovation that you have planned will aspire, okay, will grow, else it will not grow. If any one of this aspect grows down or is not popping up, then the innovation will die down. Okay, so that is how a lot of innovations do not come to the market stage. Okay, so any one of this, either desirability or viability or the feasibility, okay, any one of this will be showing a downtrend, and people are not happy or customers are not happy with that product. Okay, so same thing happens with our renewable energy sources as well. Okay, so in some cases, the viability of the devices, okay, the viability of the appliances uh, uh, are not so happy with the consumers. Okay, so in that case, the innovative all this, the product dies down. Okay. Then innovation can be either in terms of the products or the process in which we are developing. Okay, maybe in some industries we go with a new process, right? Like a semiconductor industries has some new processes and some new services that we do. Okay, so like a PV panel cleaning services are all new services that we add to the existing PV panels, right? And new models, methods, all this can be classified under the innovations. Okay, whatever small development that we come across with renewable energy can be classified under the innovations. Okay, so if I see the different types of innovations, okay, which are existing as of now, they can be classified mainly into four types. Okay, incremental innovation. Okay, incremental innovation. So now a lot of research that we do in our renewable sectors are with respect to this incremental innovation. Okay, because see, what we do is try to vary a very small parameter of the renewable energy source and get the output performance of that, right? Like say shape change, color change, wavelength change of the radiations. Okay, so like that we try to change very minimal, very small parameters, delta x parameters, and try to see the improveness or efficiency of the system. See, that is not going to make a very drastic change in the innovation, because it is a very small incremental changes in the parameters, right? So the core functionality may not change. Okay, the idea is the core functionality may not change, but still we can see the improvement as we see in our papers. But as such, the core functionality may not change. Okay, and it definitely adds new features to the to improve the competitiveness. Okay, then there comes the disruptive innovation. Okay, disruptive innovation. So here, a completely new, say, like in till now, PV panels are done with silicon cells, right? Now we use perovskite cells to develop the power, to generate the power from that, right? So that type of innovation, we call it as a disruptive innovation. Okay, it is going to come and it will change in large way. Okay, that type of innovation is called a disruptive innovation. And sustaining innovation is a combination of incremental and sustaining development to exist in the market. So a lot of companies have different types of PV cells, right? They will claim that some has say 15%, some has 16%, some has different lower amount of heat losses, and they are trying to sustain in the market by changing small incremental changes, and some small in addition some sustainable development like efficiency improving, etc., right? And radical innovation is something which substantially shifts the existing paradigm. Like say, instead of power generation by PV using the PV cells, the same radiation can be used by some other materials to generate completely different amount of power generation. Okay, or different range of power. So that is radical innovation. Yeah, radical innovation. Okay, so completely change in the that is the concept itself will change. The phenomenon itself will change. That type of innovation we call it as the radical innovation. Okay, so something like say when we are using coal-based power plants, we started using PV-based power plants, right? Such type of change we call it as a radical innovation. So these are the four main types in which we can classify all our innovations that we are presently going on, or we are trying to develop. Okay, and see now a lot of renewable energy sectors. Okay, even whatever we started or anybody has started will not sustain for a long time if because of the following reasons. Okay, there it can be the design can be bad, the lack of innovation can be there, because in the existing market we are getting good amount of PV panels, solar collectors, flat plate collectors. But once again, we also try to start the company with same set of background and lack of innovation. Definitely we are not going to sustain in the market. Okay, so many examples I can tell with respect to the commercial goods which are being used in day-to-day life. But with respect to renewable energy sources also, we can find a lot of companies are dying down now because of this lack of innovation. Okay. See now, innovation goes with design thinking. Okay, so design thinking is one of the very important concept what the companies are presently, any company, okay, any innovation company that are presently working on. So whatever company which are growing now, or which is showing a higher trend in the market, okay, in terms of financial or in terms of name, fame, etc., all have a team of this design thinking. Okay, because ultimately this design thinking is going to lead to the innovation. Okay, so that is the idea. So once we follow the set of procedures on this design thinking, then automatically the innovation part is going to improve. Okay, so this is to make a product or service, okay, functional and usable by providing novel solutions. You automatically see, you can compare it with the research work that you are doing, right? So when we start some research work, we have to get some novelty aspect in that research what we are doing. So same way, when we are thinking about the product, making a product, uh, for making it usable for the end customers, it should give you a novel solution. Okay, the customer should feel that it is something new compared to the existing functions. The bridging the gap with the existing models, okay, or existing uh, maybe existing panels can be added with the new panels to increase the efficiency, okay, or specific needs of the devices, okay. So when I'm doing a design thinking process, I should be able to give something new to the customer, okay, whoever is going to use it in terms of power or any way. He should be able to feel something is new, and it is able to shorten the present gap that is existing in his device, and it is satisfying some specific needs. Okay, so innovation is one of the phase of the design that introduce newness. Okay, so design thinking is not as we say, it is not a linear way. Okay, we cannot directly get the solution of any product. Okay, we cannot see any device. Once you are planning to maybe establish some PV panels, okay, PV panels to the your roof, then see directly nobody is going to buy your PV panels and directly install it, right? So they are going to do some survey for that. We have to make the consumers to understand that this is something new, okay, and make them to understand that this is going to decrease their power consumption, money, etc., right? So a lot of process is involved in that. Okay, so a non-linear and iterative process to understand the customer's need, because we are going to satisfy the customers at the end. So it is a non-linear and iterative process. Define the problem to design innovative solutions, and helps in value-driven solution for complex problems. Okay, so one by one we will see what this means. Okay, what this means. So design thinking involves multiple reviews. Okay, so we cannot get the solution in a single stretch. It requires multiple reviews, then the iterations, repetitions of the work, and revisions if possible. It is the human-centered or end-user-centered approach to solve the problem with the innovation. Okay, and it helps to give the solutions for the complex problems. Okay, and helps to identify and understand the problems quickly, explore new alternatives, and give the economically sustainable solutions. So in our country like India, design thinking is very much essential, okay, in order to come up with a new product. Okay, and it can be used to improve and innovate the products, services, new apps, etc. Okay, so now a lot of examples are there with respect to how the design thinking works. Okay, so a lot of examples like smart fridges are there. All global leaders follow this design thinking procedure. Okay, so see now design thinking goes with the critical thinking aspect also. Okay, critical thinking. So this is one very famous example that we come across in the problems during the critical thinking process. Okay, so maybe you can also go through this problem, okay, and see if you can able to give the answer for this. Okay, so yeah, a truck driver tried to pass through through under a bridge, but the truck was tall that it got stuck under the bridge. Okay, so that means the truck was a bit tall, and the truck could not go under the bridge. The driver was unable to move the truck in any direction, and it was causing a long traffic jam. Now, see, this is now we cannot break the bridge for uh, making the truck to pass, right? So we should come up with some new idea, a practical idea, a money saving idea, and a time saving idea, where this truck can easily pass under the bridge, right? So a set of engineers, all team workers came and started discussing about this. But there is one person came up with a very simple solution based on his critical thinking. Okay, so hope many might have gone through such critical thinking exercises. Okay, so what he suggested was to lessen the air of these tires and decrease the height of the truck, so that the truck can easily pass under the bridge. So idea is what we are about to get the lesson from this is there should be an out of box thinking when we are designing a new model or a new product or any service. Okay, so this is one simple idea to demonstrate how the out of box thinking can help a big to solve a big problem. Okay, so there are tame problems which where the problems are well defined, and we can get the relevant data and solve the problems directly. But in many cases, the problems are not direct. Okay, the problems are not direct. They are not clear. They have very irrelevant information, incorrect information, unclear information. Okay, human interventions are involved. Okay, so for example, if I want to install a a windmill in our houses or in the area, okay, in the area where there are 100 houses. So now if I'm getting a project to install some 100 windmills, small windmills in our houses, now immediately I cannot go to the market and get the windmills and install in each houses, right? So now I have to go and interact with the people there. I have to take the readings there. I have to monitor the weather conditions there. Then I have to come up with a new model of wind turbine for a suitable wind speeds, and then only I can use it, right? So such problems are a wicked problems, okay, where there is no direct data, where I cannot directly go and install it. I have to collect a lot of information for such type of projects, right? So there are, as per the Stanford design thinking process, okay, there are 5 stages in which we have to follow this design thinking. Okay, there are 5 stages in which we have to do this design thinking. Many other methods are also there. Okay, many other design thinking process are there, but the Stanford design thinking process is a well-known and renowned process used in many industries and research purposes. Okay, the stages are stage 1 is empathize. Stage 2 is define. Okay, define the problem, ideate the problem, make the prototype of the model or the problem, then go for testing. Okay, so these are the 5 stages suggested by Stanford design thinking process. Okay, so when we start doing any product development or any innovation, then at least all this should be this route has to be followed. Okay, then only we can confirm that the product that we are going to get, okay, is foolproof, or it can sustain in the market. Okay, so first thing is, the stage one is empathize. Okay, empathize means we have to think ourselves as the customers. Okay, so for example, I want to install a wind turbine in my house. Okay, and say I am the man going to develop the wind turbine and I am going to sell it. So in such case, I should think myself as the customer and try to understand why it is required. Okay. See, now this has to be done without any prejudice. Prejudice. Okay. Prejudice means since I have got the idea, I should not uh, try to implement forcefully. Okay, so because see, whatever ideas we get, we try to force those ideas on others, right? Because we may think our idea is great, but it is not like that. So it has to be empathized first. First, we should go and stand ourselves in the shoes of the customers and see whether the idea that I am getting or the innovation that I am trying to do is useful to the customer or not. Okay, so such type of analysis has to be done. That process is called empathize. This is very important process. So once we do this, immediately we can understand for whom I am going to develop the product. Okay, for whom I am going to develop the service. Okay, it can be either a wind turbine or a PV panel or any other power devices. Okay, so for whom I am going to develop. Okay, so now there was a recent innovation where power was harnessed using the shoes while walking, right, or trekking. So see, such type of power is a very low power, but still that idea was utilized and it came out as a product. And a lot of people and army are using such shoes for generation of small power that can be used for making detecting some or powering some sensors. Okay, so such type of empathizing should be there. Okay, so we should stand in the shoes of the customer and try to see whether our idea is a useful idea or not. Okay, so this is called human centered approach. So understand the customer needs, and if possible I have to go and conduct interviews with different stakeholders. Say I'm generating any APV power panel, so I have to go and check with different customers whether this will be useful in any way uh, to your power usage or not. Okay, so such type of interviews, such type of talk, okay, has to be done first. So this can be done by using engaging, observing, watching, listening, etc. with the customers. Okay. So examples are installing micro wind turbines, solar panels for household purposes. So we have to go and just check if it is feasible for them or not. Okay. And difficult as the end. See, this process is a difficult process because nobody is going to entertain you immediately if we say that we have come for some purpose, some business purpose. But we have to start engaging with them honestly, and we have to leave all the preconceived ideas that we have and genuinely listen to their thoughts. Okay. Then comes the second stage. We call it as a defining stage. See, now with empathizing, okay, that is after discussing my idea with the customers. Now I have got a lot of data. See, I'm not going to, I am going to discuss with many number of customers, say 100, 200 like that. So now I have gathered the data. Okay. Now with that gathered data, next stage is I can define what I want to do. Okay, so now idea is there, a general idea is there. Now I have gathered the data with the customers. Now next is I can define the problem. Just like how in research we define the objectives, right? So same way here we have to define what I can make for them. Okay, what type of product. now I can focus on what type of product I can make for these people or for the customers. So these are called connecting the dots. Okay, connecting the dots. So I would have got the information from different customers on different variety of problems related to power issues. So I can connect the dots and try to assimilate those knowledge. Okay, try to synthesize that knowledge and use that knowledge to define my problem. Okay, to provide the real problems, customers will provide the real problems, and with that real problems I can come up with a new product or define a new product. See here, very important point is, okay, many startups that we are seeing in the present days, right? Many are started. See, like, see, out of 100, only 17 to 20 are sustaining. Okay, sustaining means at least at the up to the end stage. Okay, till the development of the product level. Most of the startups will die in this stage itself. Okay, they cannot sustain because they will misinterpret the gathered data. Okay, misinterpretation of the gathered data. So that means whatever end user wants, we are completely going against that. And once we come up with a product, okay, which are not useful to any of these customers, then automatically that innovation is going to fail. Then this is also on the other, after defining, this is the third stage, ideate. Okay, so here that means until now I got the data. Using the data, I have defined some problem. Now here the creative part of the design thinking begins. So that means I can use my ideas that are required for the product, okay, to devise the product. So generating ideas. So here we have something called diverging and converging technique. So this has to be done as a group. Okay, so a lot of ideas given by the group has to be taken into account. So it can be n number of ideas, 100 number of ideas to solve the problems that has to be taken into account. So this is what we call it as a requires creative mindset. So whatever ideas given by the team, our team, okay, after gathering the data, that has to solve the problem. Okay, ideas to solve the problem that has to be considered, and we have to adopt no wrong answer policy. Okay, no wrong answer policy means whatever ideas people are telling or our team is telling, design thinking team is telling, that has to be considered and assessed one by one. Okay, so there can be, say, some 10 ideas, 10 different types of ideas to solve the problem. So all these ideas has to be considered, and okay, and there should be a no wrong policy. So there can be any number of obvious and non-obvious ideas. Okay, and after discussion we should converge. Okay, we should converge to the most advantageous idea. Okay, so that will come up with next stage in the prototype. Okay, so once we converge to the best possible idea, then we go to a making of a prototype. Okay, so prototype is a first model or archetype of the solution or the product. Okay, so first model of the product. So this can be made with any resources that we get. Okay, it can be made with a cardboard, it can be made with a need diagram, it can be made with a working any sheets, okay, any available sheets. So but that prototype has to resemble with the product that we are going to develop. Okay, so this stage is called prototype. Okay, so this is the prototype. So here we are practically making. So here only in many projects you might have you might have gone through the word TRL. Okay, so TRL refers to the technology readiness level. Okay, so technology readiness level means we should be in this stage of prototype. Okay, after developing this prototype, what is the level of our technology? Okay, so this is called technology readiness level also. Okay, so here our prototype is ready, but still we have not tested it. Okay, we have made the model of the prototype, which is closely resembling with the final product that I am going to develop, and we will be checking its maybe the feasibility, viability, and practicality of it. And we will be doing some small test. Okay, so no huge investments are required. See, with this, we will at this stage only the funders who are going to fund our startups. Okay, they will be interested at. Okay, so we should be at the level of this prototype. Then only the funders will be ready to give the money at this point. Okay, then then comes the testing. Okay, so whatever prototype that we have made, okay, we can either give it to the customers. Okay, so maybe some power, the wind turbine power plant that I am making, okay, newly, I can give it to some customers and ask him to test it or put it in his rooftop and see the suitable amount of power is getting generated or not. So their feedbacks, okay, not only one customer, you have to give it to many people and check for such a viable feedbacks. Okay, check for the feedbacks and see at this stage you can decide whether the product is having the business potential or not. Okay, so again, see, every stage is an important stage in design thinking. So at this stage, it can be found whether it is having a business potential value or not. Okay, then if not, okay, so we have to identify the challenges faced by the customers. Say if there is no wind velocity, the power generation by the wind turbines will be less, right? So these are the challenges now. So now how to overcome such challenges? And we have to take the positive aspects of the solution from the customers. Okay, so with all these stages, we have to try to maybe implement again, or we have to go to the previous stages like define stage if our problem definition is not correct, or in the prototype stage if maybe a small changes in the final model has to be worked. So we have to go to these old stages and again reiterate. So that is what I told. Design thinking is a non-linear process. Okay, so when you are coming up with a final product, okay, it should be a foolproof, a very good feedback given by the customers, and a fine product at the end. Okay, so such type of products only will sustain in the market. Okay, so these are the five stages of the design thinking. Okay, so in just what I would like to conclude is design thinking is an explorative process. Okay, so at any point you can come back or move forward and try to explore with different ideas, okay, or different thoughts. So it is an iterative process, and this cannot be done as a single person. Okay, because when you are starting a company, you will be doing with 2-3 people. So it has to be a collaborative work, and it should be empathetic. Okay, the first stage I told, and user centric, and we have to get the feedback through various actions, and we should be able to create the value for the end goods. Okay, see now these are the small okay, thoughts about design thinking. So when we are starting with when you are developing a new product, so these ideas are okay, very much essential. What I would like also to concentrate here is most of the energy generation products that we have in our present day-to-day life. Okay, what we are using in our present day-to-day life, the power consumption by such devices are less than 10 watts. Okay, you can see here the dotted line I have shown you. So daily we use this laptops, daily we use these mobile phones. Okay, daily we use some sensors. Okay, some pacemaker sensors. Okay, all these small devices, they consume maximum of 10 watt. Okay, 10 watt of power. Other than that, if we go with something like oven or higher energy consuming device, these are not our daily day-to-day life type of energy, right? Maybe daily we use some TV appliances, some 40, 60 watts. Okay, so maximum 100 watts. Okay? More than that, we will not go beyond. So idea is lot of innovation prospects exists in development of power of such type of low power devices. Okay, low power harnessing energy for low power devices. Okay, a lot of innovation exists because all these are already existing. Okay, we have a lot of power plants, we have jet engines, a lot of nuclear power plants, etc., for generating power of 1 terawatt, etc. But there is a lot of potential, okay, business potential or innovation potential in getting the power for this small power appliances. Okay, so I feel that we should concentrate on such type of energy harnessing. Okay, harnessing for low power appliances. So if I show you a small chart again, see now we have 10 watts cell phones in 1 watts and micro watts. Okay, see these are not very big power. These are very, very small power. So why not some innovation be used on power development for such devices? Okay, so now a lot of people are doing it. Okay, energy harvesting for low power devices, okay, are being done presently, but we should also start doing it. Okay, we should also start thinking about it. So okay, so now I think I will show some some videos that I have collected already. Okay, the small recent innovations which are happening in our present time. Okay, so this is something called uh, see this is okay. So see, this is a very new idea by somewhere in Netherlands. Okay, so see, they have used the idea of a sunflower. Okay, and see, present TV don't have the technology for tracking, right? So they developed some devices. Okay, which will spread his this patterns, okay, leaf patterns, and directly they can get tracked by using the sunlight. Okay, so in this way, the energy harnessing by this smart solar flowers will be maximum. See now, as I told you, a lot of problems are there with respect to the different stages that we have seen here. Okay, so see, although a lot of design thinking aspect has gone in, but still this may not be very much useful in places like hugely where there are huge crowds, etc. So there's somewhere in the open cases, okay, such products will be useful. So we have to see where such types of devices are feasible. Okay, so as of now, this type of innovation is are being developed. Okay, so which will spread its petals upon seeing the sun. Okay. So okay, so there is a concept. See, we would have seen wind turbines, right? Wind turbines with three-bladed or souvenir turbines, horizontal axis turbines, vertical axis turbines, right? So there is one group that is working on this bladeless wind turbines. Okay, see, this is something like a disruptive type of innovation. Okay, so now no, without any blades, they are trying to develop the power from the wind. Okay, so it is just harnessing. So this is just directly installing it in any places where there is a good wind capacity. So this works on the vortex shedding mechanism. Okay, so when the flow happens over this cylindrical turbines, plateless turbines, there is a vortex shedding mechanisms, and automatically this cylinder is going to vibrate, and because of that vibration, that has some piezoelectric effect or generator accordingly designed, and it is going to generate the power from that. So this is a new concept which is being developed by some of the research groups. Okay. Okay. I will be giving these slides. You can see it later, or it is available. Okay, it is available in the other videos also. So this is one type of innovation that people can go ahead for power generation purpose. And see, these are presently being harnessed. Okay, so these are called floating solar power plants. So even our own country has a lot of solar power plants, okay, floating solar power plants, uh, ranging from megawatts or 100 megawatts to very less up to 2 megawatts. So this has some direct advantage, like cooling can be avoided, efficiency is higher. Okay, so such type of power plants are installed by our NTPC itself. Okay, so this is one new type of innovation that is coming up with renewable energy. Okay, so these are floating solar power plants. Then see, other very small cases are also available in present. Okay, small where energy harnessing are at the micro levels. Okay, so very developed countries like Japan, etc., are using the pedestrian energy for generation of small powers. Okay, which can maybe charge mobiles for some households. So they use some piezoelectric tiles. Okay, they use some piezoelectric tiles in the platforms, and when the pedestrian walk over these piezoelectric tiles, they generate power. Okay, not a big power, as I told you. They are not in megawatt range or kilowatt range, in some watts. Okay, milliwatt to watts. And as I told you already, there are some footwears which are used as energy harvesters while walking or while jogging or while trekking. Okay, or during army purpose. Okay, army people use this energy harvesting to detect some, to activate some sensors. Okay, similarly, there are some acoustic energy harvesting device like Helmholtz resonators, which will oscillate the piezoelectric strip and generate the powers in microwatt range. And a new concept is coming up, something like making an artificial tree. Okay, making an artificial trees. See, artificial trees, when wind moves over these artificial trees, they move very rigorously. Okay, so they want to, some research group wants to utilize that movement of the artificial trees, and see, it has a very large drag also. Okay, artificial trees will have a large drag, so entire energy, wind energy, can be converted to the electricity. So in that way, artificial trees are being used for tapping, to tap the power by using its vibration energy during the wind flows. Okay, and some underdeveloped countries have used plastic bottles for illuminating the buildings. So these are very small innovations, but very useful for those places. Okay, so solar PV glass panels for buildings, And now commonly there are silos, okay, silos which store sand, okay, sand in very large scale. So that sand or any other chemical, okay, it stores the sensible heat during the daytime, and when during the night time it can be reutilized. Okay, so such type of thermal systems are available. Okay, so this is also one more a new innovation presently going on in many countries. Okay, so a lot of such innovations are presently happening. Okay, so it is time that we also can think of some type of innovation startup related to this. Okay, and here I will not go further. These are some more additional things that we can see in the video. Okay, and some links are given where you can see whatever I have given in the slides. And say I would like to thank AB Unitan, okay, from where I collected all the materials. So I got interest with this innovation topic once I attended his lecture in IAM. And see, although my research is not in this field, innovation, but still I thought I will take up this area and go into it. So these sources I felt very much useful in reading. Okay, so if interested, you can also go through it. Okay, yeah, thank you for your patience hearing. Any questions, Subramanian?
Thank you. Participants, I think there are any questions, please. I'm just enabling the chat box as well as
Okay, I can see
this
one
one.
question. Okay, so what I do now, someone...
Nagaraj, Nagaraj, please proceed.
Hello, sir. Good evening, sir. Myself, Nagaraj.
Nagaraj, yeah, I remember you. Yes. How are you?
Thank you so much, sir. I submitted MTech thesis under your guidance.
Yeah, I
I
know.
think you.
Yeah, we got a paper also.
Yes, sir. Thank you.
Yeah,
Thank you for remembering me, sir. So
yeah,
the thing is,
okay.
sir, you explained the importance of design thinking process for the product development.
Okay,
So my question is, when we would like to formulate a solid problem statement, so we have
okay,
to follow certain empathization methods,
correct.
particularly in green energy or renewable energy sector.
Okay,
Scenario is very clear because there is a standard energy demand, population growth, lots of reasons, globalization, etc. So my
correct.
question is, what are the suitable empathization methods to collect data so that we could able to formulate a solid problem statement?
Correct. See, as you rightly told, uh, see this type of design thinking models go well with a smaller scales. Okay, smaller scales where the customers directly come into the picture. Okay, because see, in power sectors already we know that there is a demand, right? There is a requirement, power requirement throughout the world. So uh, empathizing is not required in such scenarios because I need the power. I need the power some way, some by some source, right? So different sources are being utilized for power generation. But when I am trying to do it in a micro scale, okay. See now, everything need not be in a macro scale. All power generations are some power companies are concentrating on micro wind turbines, right? Or some power companies are trying to install solar water heaters in houses, right? So in such cases, okay, for that type of aspect, okay, in such aspects, we should look into this design thinking process, okay, not in the larger scale. Okay, so this is what I understand.
Yeah. So one more, sir.
Yeah.
Since the design thinking is a non-iterative process, when we would like to approach for funding organization, they are asking TRL level 6. That means almost we should finish the prototype part. So the thing is, it should be exactly demonstration stage, or at least a flow chart with some validation results.
Okay.
Is it
Okay. See,
acceptable?
yeah. See, TRL one means it is just like a like a diagram. Okay, you are showing something in the form of a diagram. Okay, so that
Yes,
comes
sir.
under
Yes.
like a very low technology readiness level. Okay, so that all are doing now. Okay, that type of prototype all are doing. So at least you should have 5 and above. Okay, 5 and above means it is in the stage of demonstration. Okay, it is in the
Yes.
stage of demonstration and working. That level should be there. Okay, for fundings to occur. Okay, so at least it is very close to the startup. Okay, or in the stage of startup. Okay, that is what say up to 9 it will go. Okay, TRL 9.
So that means with the computational results, and I mean we can test our prototype using some computational model, so we'll get some results. So can
Okay,
we claim that this is technology readiness level to seek funding from organizations?
no, that is not possible. That will not be taken. That will not be
Okay,
taken. Okay, so it should be close to the real product.
real time. So that means we need to test with the real time
Yes,
data.
yes.
Thank you, sir. Thank you.
Okay, sir. Okay.
Sir, I have a small query, sir.
Yeah.
What is the role of IoT in this innovations in the renewable energy system, sir? Like, is we can integrate these IoT systems to renewable energy system? So how it will change that new era in coming years?
Okay, sir. So, sir, I feel as per my knowledge, IoT is coming up in all the sectors. Okay, IoT is coming from household sectors to all industry sectors. So, definitely, IoT will play an important role in renewable energy sector also. See, now once IoT is there, I can define my own conditions when power generation should, when power should get stored, when power should get consumed, when it should start and it should stop. Okay, so all this and remotely operating the sources, the renewable sources, all will come into the picture. So definitely people are working with IoT technologies. So no doubt in that. IoT
Okay,
will penetrate.
okay, sir. Thank you, sir. Any questions from audience side?
I think we have few more questions in the chat box. I think we please.
Okay.
Could you see the chat box? Was the
Yeah,
question?
yes, I can see. 1 minute. Let me. Okay, so one question is on. Can you give insight on red ocean strategy and blue ocean strategy on sustainable power generation? Okay, so by Sampath. Okay, so actually I am not aware of this red and blue ocean, but there is something called blue economy. Okay, now blue economy concept is growing up a lot. So what are all the innovation startups and commercialization that can happen with respect to the ocean? Okay, with respect to the ocean, because the ocean is a huge resources, right? So whatever economy that we are doing on the land, same amount of economy can be done. Okay, economy generation or okay exchange can be done with the ocean. So that concept is coming up under the topic of blue economy. Okay, so people are earning or trying to earn or do innovation with respect to that concept as well. Okay, so that is called blue economy, but I don't know about that red ocean and blue ocean strategy. Okay. Yeah. Okay. Otherwise, nothing. Nothing.
Any other participants? Uh, someone sent one more message on the chat. Can you suggest some alternative and innovative technologies?
Okay. See, alternative and innovative technologies for solar cooking. So that is what I told you. I think this is by Krishna Verma. Okay, so see, that is why this sensible heating, thermal energy storage concept is coming up. All right. See, now thermal energy storage are not doing in a small scale like 1 kg, 2 kg. They are doing in tons. Okay, like say some 100 and 1,000 tons. Okay, so they are using chemicals. They are using rocks, pebbles of say 1,000 tons in silos, and this heat is stored either by using geothermal, okay, because generally the heat below the earth will be higher, so that heat is being utilized, or by using solar power plants. Okay, solar power plants. Now we are getting not PV but solar thermal power plants are there. So that are being that energy is being utilized to increase the energy of that silos, okay, which is a sensible energy storage. So that can be utilized in the complete night hours for cooking or some other heating purposes. Okay, so that concept is also now very much coming up. Okay, so people are going with a very large scale in terms of thermal storage. Okay, so other than that, many other conventional methods are also available. Okay, yeah.
Sir, there is a small question, sir. So you
Oh
discussed
yes.
about that windless, turbineless wind turbine, like bladeless, sorry, bladeless wind turbine.
Yes.
And is there like any cut-in speed for this kind of wind turbine,
Nothing,
sir?
sir. No cutting speed. No cutting. See, that is the advantage of using that.
Hmm.
Bottom will be fixed, and
Hmm.
there is something like a spring mechanism, and above that, the one more structure is present. So, see, now it is not going to completely bend, okay, because of the wind, but
Okay.
there is no cutting speed. That is the advantage of using this
So
blade.
even lower wind speed, like 1 meter
Yes,
per
yes,
second, also
yes,
it will
yes,
work out,
yes.
no?
It will work. It will work. Yes,
Okay,
yes,
okay.
yes, yes.
Any other participants can? I think Dr. Ravi.
Sir.
Yeah,
Okay. So,
yeah.
thank you, sir.
Any other?
I would like to sincerely thank you for your enlightening session on design and innovations in renewable energy system during our faculty development program. Your
Sorry.
deep insights into the cutting-edge design principles and innovative technologies provided a fresh perspective on advancing renewable energy solutions. The practical examples and forward-thinking strategies you shared have inspired our faculty to explore new approaches in both research and teaching. Your session has undoubtedly equipped us with valuable knowledge to better address the challenges in renewable energy systems and contributions to sustainable development. We are truly grateful for the time and effort you dedicated to making the session both engaging and informative. We look forward to future collaboration and hope to benefit from your expertise again, sir.
Yeah, thank you all. I would also
Sir, can
like
I
to,
ask one question, sir?
yes.
Yeah, sir. Actually, you were mentioning when we are doing some research, we need to collect the data by going to customer something. Yeah.
Yes.
Actually, I work in passive cooling of buildings using thermal energy storage of paste materials.
Okay.
So I prepared a building build material which can be actually I reached up to tier level 4 actually. So now, what is your suggestion? Whether I need to approach a company or customers who are already like a
No.
builders?
See, already you are in the TRL level means
Hmm.
already you have crossed. You have crossed all these stages.
Yes.
Okay, you have crossed all these stages. That means, see, you are now in the verge of development. Okay, that is in the verge of developing the product. Okay, prototype is already there. You are in the
Yes.
verge of developing the product now. Okay,
Yes.
so see, if you have done a proper analysis of all this, okay, definitely your product will have a high demand in the industries. Okay, at the same time, if say there are some drawbacks, okay, and see now you will be going to discuss with some companies for getting the money, right? So at
Yes.
that time, if there are some challenges, some drawbacks, then try to rectify in the TRL itself.
Okay, by this design thinking process, we
Yes,
can improve it.
yes. Try to reiterate and redo the model, okay, with suggested changes. If it is completely out of the path, okay, what the company exists, then I think you have to change in the design defined stage itself.
No, sir. Actually, at lab scale, we tested thoroughly. We got very good potential results.
Then very good.
So now
that
we
means,
require some funding so that we
okay.
can do some real prototype building level.
Okay, that means you have to clearly mention that you are in the development stage. Okay, so you are looking for some venture capitalist for funding your projects.
Okay, so can you suggest like where we can approach, where we can get this?
See, recently we conducted one innovation meet here. Okay, Kerala Innovation Meet. Okay, so actually I was also part of that, where a lot of venture capitalists came and gave their what is that, their motives, okay, whom they are looking for, etc. So I will send you his number.
Okay, sir.
I will send you that person number. Okay, so see, they may call you or they may chat with you using some online mode. Okay,
no problem.
Okay, and maybe after that you can make a link with them.
Sure, sir. Sure.
Okay, I will give you the link. Okay, no problem. Because recently we conducted the Kerala Startup Mission here.
Okay, sir. Actually, I'll be in touch with you, sir. I'll write an email.
Sure. No problem.
Actually, I'm also alumni of NIT Calicut. I did my MTech in thermal sciences from NIT Calicut.
When was it?
I passed out in 2010, sir. Actually.
Okay. Maybe I was not.
Yeah,
there.
you was not there, sir. Actually,
I was not. Okay, good. Your name?
My name is Dr. R. Naresh, sir. I'm working as assistant professor in mechanical department in BRIT Narsapur, Telangana, right now.
Oh, good, sir. Very good. Very good. Okay.
I graduated this year only from full-time PhD from BITSPIL and Hyderabad campus.
Hyderabad campus. Okay.
Yes, sir.
Okay. Oh, good.
So
Good.
completely.
So please,
Actually, I'm also the Prime Minister Fellow as part of my PhD.
PMRF.
So,
PRMF
yeah,
fellow.
PMRF. Yes, sir.
Okay. Good.
Through industrial collaboration, actually.
Okay. So please visit our institute. Okay, NIT Calicut.
Sure, sir. Sure.
Now one conference is coming up in March, which is on decarbonization of India.
Sure, sir. I definitely
I will
look
send
forward
you
to
the
that.
link.
Please, sir. I will write an email, so kindly share the details.
Sure.
Investor as well as this conference also.
Sure.
Nice to hear your session, sir. Thank you.
Thank you.
Yeah. So thank you. Any other participant? Okay. No more, I think. Thank you, Professor Sarvottam Jyoti, for your insightful talk on design thinking and innovation in the renewable energy sector. Your ideas have inspired us think creatively about sustainable solutions. We truly appreciate your time and expertise. Thank you once again for accepting our invitation, even despite your busy schedule also.
Thank you. Thanks to all the audience and thanks to the organizers, Ravi and Subramanian. Okay, so anyhow, this is a new topic to me also. So I'm also in the learning stage. If there are some mistakes, please apologize. Okay.
Very much useful to all the participants. I think this is one of
the. I think this is out of what is the topics that generally are discussed, right? Conventionally, we discuss all energy related topics. So I thought I will give this today. Okay.
Thank you so much, sir.
Okay, I'll leave. Okay. Thank you.
So, dear participants, a small request from my side. So, can you switch on your video so that we can take some screenshots? So, it is necessary to upload the screenshot in our ATAL portal. So, this is for our reference only. So, kindly cooperate in this regards.
Sir, please enable the video, sir.
Yeah, already enabled.
It's not enabled.
Now, please, I think.
Now, it is, yes, sir, we can see.
Just one, if you
Just hold a,
few
hold a,
minutes. Just,
hold a second, sir. We'll take a screenshot.
okay.
Okay, sir. Thank you, first. Thank you, sir. Thank you for the cooperation. Now you can switch off your video, sir. Thank you for your kind participation, sir. So tomorrow we have a wonderful sessions on regarding that advancements in thermal energy storage systems. And he is going to handle by professor from NIT Tiruchirappalli from mechanical department. So that is the first session tomorrow, and second one is handled by Dr. Sridhar Garu. So those two sessions are very informative. So kindly support us and join and gain some valuable information from them.
Okay, Ravi. Okay. Thank you, Ananda, once again. We'll meet tomorrow.